I really enjoy building things from scratch, just like this FOC driver. My previous FOC driver took many rounds of trial and error before it finally worked well. This time, I made a new version with a completely new design. So, is this new generation driver really better than the previous one? Let's find out. This BLDC motor has three wires, A, B, and C. If wire A is connected to the positive voltage and wire B to the negative voltage, the motor winding becomes an electromagnet and pulls the rotor to a certain position. Then, if the negative voltage is moved from wire B to wire C, the magnetic field changes direction, causing the rotor to move. By continuously changing the order of these three phases, the motor rotates. This method is called six-step commutation. In the six-step method, the rotor only moves every 60 electrical degrees. As a result, the motor doesn't rotate very smoothly, especially at low speed. To solve this problem, space vector PWM or SVPWM is used. SVPWM controls the voltage of the three phases using PWM, allowing the magnetic field to change more smoothly. This lets the rotor move to positions between the six steps, making the motor rotation much smoother. However, SVPWM alone is not enough. The driver still needs to know the rotor position. If the rotor position changes but the driver doesn't know it, the stator magnetic field may no longer be aligned with the rotor. This reduces the torque or might even cause the motor to stop. That is why FOC requires a position sensor, such as a magnetic encoder or an optical encoder to measure the rotor angle in real time. Another challenge is back EMF. As the motor spins, it also generates a voltage that opposes the voltage applied by the driver. The faster the motor rotates, the higher the back EMF becomes. As a result, if the driver only controls the voltage, the motor current will keep changing, making the torque unstable. That is why field-oriented control or FOC controls the current instead of the voltage. The driver automatically adjusts the voltage to keep the current at the desired value, allowing the motor to produce smooth and consistent torque over a wide range of speeds. So, for a motor driver to run FOC, it needs three main components: a three-phase inverter, a rotor position sensor, and a current sensor for current feedback. Before designing the schematic, the first step is to decide the microcontroller pin configuration. For this project, I choose the STM32F405, a high-performance Cortex-M4 microcontroller with a floating point unit, making it a great choice for computations such as the FOC algorithm. Next, I assigned all the required peripherals such as ADC for current sensing, PWM for controlling the inverter, SPI for the magnetic encoder, as well as USB, CAN, and other communication interfaces. Interestingly, with the number of GPIOs and peripherals available, the STM32F405 is actually capable of controlling two BLDC motors with FOC at the same time. Even though this board is designed for only one motor, I still optimize the pin configuration for two motors. This way, if I decide to build a dual motor version in the future, I won't need to change much of the microcontroller configuration. Now, let's move on to hardware design. I use KiCad to design both schematic and the PCB. This board uses a two-layer PCB with a size 60x56mm. I also try to place most of the component on the top layer to make assembly easier. And this is the final design. After finishing the design, I ordered the PCB and PCBA from GLC PCB. I like using GLC PCB because everything is in one ecosystem. After designing the PCB, I can instantly order the board, source the components, and even use their PCBA service without switching vendors. Here is the result. The assembled PCBA looks very clean and soldering quality is excellent and everything works exactly as expected. I only soldered a few components myself because I already had them in stock. I also provide the Gerber file and the bill of materials in the link below. So if you would like to build the same board, simply download the files, go to the GLC PCB website, click order now, and upload the Gerber file. You can also check out GLC PCB through the link in the description. Now, let's take a closer look at the hardware. For this design, I choose the DRV-H323RH as the MOSFET gate driver and the N-channel MOSFET. This gate driver is quite compact and has a built-in regulator, so it can also supply power to several other components in the circuit. To connect it to the STM32, it requires 6 complementary PWM signals, along with AND gate signal to enable the gate driver and AND fault signal to monitor any driver faults. For the motor position sensor, I choose the AS5047, a 14-bit magnetic encoder that communicates over SPI. This sensor can measure the position of a diametric magnet placed directly above it. So, if the magnet is mounted on the motor shaft, the driver can determine the actual rotor angle. I also added connector for both SPI and incremental encoder, so an external position sensor can still be used if needed. For the microcontroller to measure current, the current must first be converted into a voltage. This is done by placing a small shunt resistor in the current path. The small voltage across the shunt resistor is then amplified by a current sense amplifier before being read by the ADC. After that, the STM32 can calculate the current using Ohm's law. The TRV-H323RH actually has 3 built-in current sense amplifier for low-side current sensing, which measures the current on the ground side of the inverter. This method is simpler and less expensive, but the current can only be measured accurately while the low-side MOSFET is turned on. As a result, when the PWM duty cycle approaches 100%, the low-side MOSFET is on for only a very short time, making the current measurement less accurate. Because of this, I choose inline current sensing for this design, where the current is measured directly on each motor base. Although the circuit is more complex, this method provides more stable and accurate current measurement under different PWM conditions, making it ideal for FOC, which require precise current sensing. I use a 0.01 ohm shunt resistor together with the INA240A1 current sense amplifier, which has a gain of 20 volt per volt. This means the voltage across the shunt resistor is amplified 20 times before being read by the ADC. To make firmware development easier and to communicate with other devices, I also added USB full speed and CAN bus to the STM32. For USB to work, the STM32 requires an external crystal oscillator. For the CAN transceiver, I use the TGA1051DK. After all the components were soldered, the next step was to make sure the hardware was working properly. I start with a simple blinking LED program to verify that the microcontroller was running correctly. All I had to do was connect a USB Type-C cable for power, then connect a ST-Link to the 3-pin Pico Blade connector to upload the firmware. After the firmware was uploaded successfully, the LED started blinking as expected. This confirmed that the microcontroller and the basic hardware were working without any issues. The next test was running SVPWM to make sure the gate driver and MOSFETs were working correctly. After connecting the BLDC motor, it successfully rotated in open loop mode, just like a stepper motor. I made quite a lot of changes to this new firmware compared to the previous version, making future development easier and more organized. After several weeks of work, the board can now run current control, speed control, and position control. It supports not only sensored FOC, but also sensorless FOC. I also updated the communication protocol, allowing the port to be controlled directly using a Python script. From there, I can send set point, change motor configuration, read real-time data, and plot different variables to make tuning and analysis much easier. I think this part is much better than the previous version, especially in the current setting section, which is one of the most important part of FOC. Of course, there are still a few things I want to improve in the next revision, but overall, the result is exactly what I was hoping for. Based on the component price from LCSC, the total cost for one port is about $28.58, not including the PCB, assembly, shipping, or taxes. What do you think? With the specification, is the price still reasonable, or is it a bit expensive? In the next episode, I will talk more about the firmware of this new port. Thanks for watching and see you in the next episode.